Okay. Continue. You got that? Weight. So, the things to look at. I'm sure you could probably guess the meaning here. Gravitational force is the force from gravity. So, it is the force of attraction between all matter. That's basically the definition. You can write the second sentence if you want, but this is enough for the definition. All I have to say extra is that normally it's only felt when the object is extremely large, like the Earth, the Moon, the Sun. But usually, you can't really see the force pulling matter together. The first sentence is enough. You can write both if you like, but the first is enough for the definition. Question: is gravity strong or weak, would you say? It depends. But compared to other forces then? It is weak. Hand me the bottle of water. Think about this, okay? Every part of the Earth is pulling this down. The whole Earth is pulling this down. And I can pull it up. Okay? So gravity is a very, very weak force. It's the weakest force in physics. It is the weakest force in physics. It's what keeps you on Earth. So it is an important force, although it is weak. So the weight precisely is the amount of gravity force. That's all the weight is. So it's how much gravitational force is experienced. What is that? That blue thing on the table?
It's wet dishes.
Oh, okay. I thought it was some kind of strange chocolate bar. Okay, have we got that? Yeah. Can I? No, you're writing. That's okay. Okay. What else is there to say? Really, not much else to say about it, so we'll just continue on to the next slide then. So let's find a formula for the weight on Earth. Not too difficult. Okay, so here is our person here falling down. There's a force acting down on this person, and that force is the weight. But Newton said F is equal to ma, and we said last time that the A due to gravity is equal to G, the 9.81. So that's really it. We have this very simple formula for the weight. The weight is just equal to mg, nothing too special there. Yep. Okay. So we have our formula W equals mg, where W is the weight, m is the mass, and g is the acceleration due to gravity. Okay, so here's a very simple one for you to do. It should only take you a few seconds. How much does a 2 kg book weigh? So if you've got your calculator, you can tell me, or you could do it in your head. It's not too difficult. Yeah. 19.62 newtons. Got that? Okay, here's another one. How much does a 2 kilogram physics book weigh on the moon? And by the way, the gravity is about 6 times smaller. The force is 6 times weaker on the moon than it is on the Earth. So what answer do you get here?
3.2.
Yeah, 3.27 newtons sound about right. A 2 kilogram physics book weighs 4 newtons on an asteroid. What is its mass? What is the mass of the book? 2 kilograms, yeah. I'm just trying to trick you here to see if everybody's awake. It's just a silly question, never mind. Which will hit the ground first? Yeah, the bowling ball. But there's a small problem with that, because if you look at the picture, there's the ball, there's the feather here. Both of them, what's the U? 0. The V we don't know. We think the A is a G or minus G. The T we don't know, and the S is whatever the height is. Let's just say 1 meter. And of course this is wrong. There's something wrong here, because it looks like they have the same information, which means they should have the same time, but of course they don't. So what is the mistake? What's the problem here? The mass is different, but that's not actually... I suppose my question is, I think these are the same for both, but really they're not. Which is the one that is different?
Acceleration?
Yeah, because the U, okay, has to be 0 for both. And the S we can see has to be 1 for both, or rather I should say minus 1. So it was wrong for me to say the acceleration is G for both. But then you might be thinking, but I said last time that when something is falling, the acceleration is G. Well, what's happening here is that this is falling and this is falling, and it has a weight 1 and this has a weight, we'll say, as well. But what's different in the picture is that this one has another force acting this way. What is this force? And it's not really present here. Resistance, yeah, why? Well, from the air. The air is going to act as a sort of upward force. We call it as a resistance force or a drag force. And this has the effect of making the W, making it smaller. So you know that F equals MA, which equals MG, so A equals G. But if there was another force here, you would have F, which equals MA, that will equal mg minus the drag force, because this weight is getting subtracted by this acting in the opposite direction. So it means the acceleration instead will be g minus whatever, drag force over m. But that's getting a little bit too messy. I don't need you to write this down, because I'm going to talk about this in more detail. You can write something down if you want. So far, we've only looked at one force, which is the weight. But in real life, there's actually going to be more than one force acting on an object. Like in the picture I just drew, we had two forces acting on it. Here is an example, and you can draw this with a car. So there are two forces acting on this car. This one called the thrust, which is what drives the car forward. But this one here called the drag, which is trying to slow the car down. In the beginning, which is greater? Which is bigger of the two in the beginning?
Drag.
No.
Drag.
Yes, because the car successfully moves forward. At the end, what has happened? Is the thrust still bigger when the car is travelling at its maximum speed? No, because what happens is, as the car goes faster, what will happen to this force? Bigger. Why though? Like, you know this, when you're driving a car, it kind of gets harder and harder to go faster and faster, because this is becoming bigger and bigger. But why would it be becoming bigger and bigger? Huh? Yeah, but why? Like, you know, like, but why is it getting bigger to reach this? Yeah, but why should it get bigger? You know, it is resistance, and it is getting bigger, but why is it getting bigger? Yeah, but why? Why? Yeah, but why does that make more drag though? Why isn't the drag the same?
Because they're moving against something? Against
yes,
the air?
Yes, this is the key. We're moving against the air. And the faster the car moves, the harder it's hitting the air. You see, the car is pushing its way through the air. At the beginning, it's easy. But as the car's going faster, it's harder to push through the air. The car is literally pushing its way through the air. If the car was driving in a mountain, there would be less drag because the air pressure is less. There's less air around. If the car was driving in space, there'd be no drag because there's no air. Of course, the car wouldn't work, but you get the idea. Yeah. So this gives us an idea here. When the car moves faster and faster, this will get bigger and bigger. It'll keep getting bigger until it equals this force. And then that's sort of the limit that what the car can do. This gives us something called terminal velocity. Oh yeah, the only thing you really need here is this picture is a useful picture if you want to draw something. You can draw a stick man running or something if you don't want to draw a car. Okay, can I continue? Yeah, yep. Okay, so any guesses now what the meaning, if you look at it you could kind of work it out if you know the meaning of the word terminal. What could terminal velocity mean? Well actually I should check, do we know this word terminal? I don't know if this is, no? Are you sure? I'm sure somebody knows it. Terminal? Where have you heard the word terminal before? The airport, yes. Yes. Now, of course, I don't mean airport velocity. Terminal, if you were to try and guess the meaning, think about the airport, what could terminal mean?
Section.
Could mean section, what else?
Station.
Could mean station, yes.
Is the velocity in a specific time?
Final.
Good, but no. Now he's got it over here. If you think about it, the terminal is, in English, terminal means final. So it's called the terminal because, you know, that's the end of the journey. Now at the airport, it's also the start of the journey as well. But for example, for the bus stations, you only call the last one the terminal because a terminal means final. You also know you have something called terminal illness.
Yeah, I'm thinking of that.
Yes, so a final illness, yeah. So here what might terminal velocity mean? Final velocity. But it's not just final, it's also the final and it can't go past it. It's like a maximum velocity, it's the limit. So in the picture here, when the drag is equal to the thrust, the car has reached the terminal velocity. So terminal velocity is the maximum possible velocity a free-falling object can have. We usually use terminal velocity to describe objects that are falling in space. If you jump off the top of a building, you will fall, and you will fall faster and faster, but at some point you reach a maximum speed. This does not make you safe, it just means you're not going faster or faster. Yeah? And I have a picture here. You see, here's the example of the parachuter. He jumps out of the plane and he falls and he falls and he goes faster and faster and faster, but at some point he just travels at a constant speed because the weight has equaled the air resistance acting up. We were talking earlier about how the car, if it's moving faster, it has more of a drag force. In fact, Drag force is proportional to the speed, or a speed term. What I mean by that is normally, if the velocity is doubled, it would mean that the drag force is doubled as well. That's what I mean by proportional. Now, in fact, in real life, it's actually worse than that. In real life, if you double the velocity, you actually quadruple the drag force. So if the car goes twice as fast, then the drag has increased 4 times. We do not have to worry about this in our problems, because in fact this is too difficult to do in our problems. It's mathematically very difficult. Instead, usually we imagine the drag force is constant, or that it changes a little bit. But it actually changes in a very complicated way. If you study engineering next year, you will understand in more details how the drag force changes, but we will not do that here. Yeah. The terminal velocity is a thing they sometimes ask you in an exam, so just make sure you have this sentence for sure. Cats have a very low terminal velocity. What this means is when a cat falls, it very quickly reaches its maximum speed, and it doesn't keep falling faster and faster. So, for example, I think it's 4 meters. So when a cat falls from 4 meters, or falls from 40 meters, the speed at the end is actually the same, because the cat has reached its terminal velocity, I think, after 4 meters, and then it's not gaining speed anymore. I mean, obviously it's still falling, but it's falling at a constant speed. So this is why you hear these crazy stories of cats that fall out of planes and they're still okay.
Is it real?
I was told it was real. I have not conducted an experiment. They don't like people doing these types of experiments, so I guess we can't really know for sure. But I believe it's only 4 meters.
How is it still staying after the landing?
Well, I mean, my point is, falling from 40 is the same as falling from 4, because it's reached its max.
They're the same speed.
Yeah, they're the same speed when they hit the ground. It's reached its maximum speed.
Oh, so it's a low speed.
It's a low terminal velocity. Because cats can do stuff as they fall that limits their speed. They're able to do things which is quite impressive. Like if you drop a cat upside down, it is able to turn around as it falls. Yeah. This sounds easy, but this is quite difficult to do. You know, I'm sure if I dropped you upside down, you would not turn the right way around. Because in your head you're thinking, oh, if I fall, I'll just turn around. But how? You have nothing to push against. You know, you've nothing to hold on to turn. You know, but cats are able to do this because of the way their bones are. They can rotate it in a certain way that lets them turn around. You can watch slow motion videos of this on YouTube if you type it in. It is quite interesting because I think that they do something where they twist their body in opposite directions. It's hard to explain, but you'll see it if you watch a video. So in other words, cats can do things as they fall to reduce their terminal velocity and also turn them the right way around as well. Okay. So let's look here. This is just a short question just to make sure you understand everything here. A car of mass m starts at rest and accelerates by acceleration A because there's a force from the engine. The driver keeps his foot down but does not continue to accelerate forever. Why not? Well, what's the reason we were saying? Why does the car not keep getting faster and faster, even though you have your foot on the gas? Reaches the terminal velocity, yeah. What could you do to the car to try and increase the terminal velocity, to make it a bigger number? What things might you be able to do to the car?
The shape of the car?
The shape of the car is important, yeah, because you can have it push through the air easier. Of course you can make the engine more powerful, but maybe this isn't the easiest thing to be doing. Anything else?
Weight.
Yeah, you could reduce the mass of the car. That would help some too. I think the shape is probably the most important factor for the drag of the car, the shape of it. You want a smooth shape, not a flat shape to the front of the car. Okay. A euro coin is dropped from the top of a 100-metre building. How long would it take the coin to hit the ground? Just a very small question, and then in a moment I want you to tell me, if you did this in real life, this experiment, would the real answer be bigger or smaller than the answer you just calculated? Okay, so calculate the time, please. How long will it take for the coin to hit the ground? You have your UVATS information, so you can get this. Let me open up the calculator. There. Got that? What formula should you use? Yeah, S equals UT plus a half AT squared will do nicely. You got an answer? You have one. Do you have an answer? Is it really? Okay, I believe you. Did you have an answer, Audrey? Yeah, what did you get?
4 seconds.
Yeah, about 4.5 seconds. If you did this in real life, would you get this a bigger or a smaller answer than this?
Bigger.
Bigger than this. Why?
Because they'll reach terminal velocity and the speed will increase.
Yeah, so it'll take it longer to cover the distance then. Yeah, good. Okay. Alright, so these are all kind of easy questions to begin with. But now we have a more interesting one. So so far we've been doing easy ones, but we've not done an example yet where we have to deal with a drag force. So far everything has just been falling freely. But now let's be more realistic. We have a steel ball, and of course I think steel is EE, isn't it? Yeah, disgraceful. You have a 100-gram steel ball, and this is dropped into a beaker of oil. You know, like a tall tube of oil. So, of course, if you drop it, it will experience a drag force, because, you know, it has to move through the oil. So as it moves down, the gravity's pulling it down, but the oil is pushing it back up. It's 80 centimeters deep. Calculate the average drag force experienced by the steel. Oh, see, I got to write this. If it takes 10 seconds, and now it's changed again. Okay, so I'll draw the picture. I think I'll do this one with you. So this is what we have. We have something like this, full of oil. We have our ball on the top. This is 80 centimeters, and it takes 10 seconds. 10 seconds is a long time to move 80 centimeters, so you know it's moving down quite slowly. Okay. Now, there is two forces acting here as it moves down. So I'll just draw it here. Obviously there's the weight, which we know is equal to mg. So we have our weight. And what did we call this force here? This is called the drag force. Now we have a small problem though. At the very beginning, the drag force is 0 newtons because it hasn't passed through the oil yet. And then at the very end, you have a drag force here, and this drag force is a maximum. Why is it a maximum? Well, because it gets bigger and bigger as it moves faster and faster, so it's biggest at the end. So the question is, which D do we use in our calculations? Should we use this one, or should we use this one, or should we use something else? Well, what we can do is we can say that the drag is roughly equal to just the drag average. So rather than using two values of drag, we'll just use one value, which is the average, which we'll say is roughly 0 plus the drag at the end over 2. So we'll just call the average drag force, we'll just call it drag. But I want you to understand that the number we get here doesn't represent this, nor does it represent this. It represents an average for the journey. Okay? So for this question, I'm going to simplify it. I'm going to assume the drag is roughly equal to a constant, which is roughly equal to an average drag force. Okay? Alright, so now that we have that clear in our head, let's start calculating. Let's get the acceleration first. Do I know the U? I do. What is it? 0. Do I know the V? No. Do I know the A? Think carefully. I do not know it. I do not know it. It's not minus G, because it's not fallen freely. So I don't actually know the A. Do I know the T? Yes. And do I know the S? Yeah. What will give me the A? V squared? V squared equals U squared plus 2AS. That's a 0. No, that can't work. S equals? Yeah, okay. S equals UT plus a half AT squared. Gone. That and that makes a 50. So I have 50A equals minus 0.8. So A equals minus 0.16. So 0.016 meters per second squared. So it's a very small acceleration, quite small in size. Okay, that's good. Now that we know the A, how could we work out the force? What is it? Yeah, we could say F equals MA. Do we know the M? 100 grams, so we know the M. Do we know the A? We do. So the M is 0.100 times minus 0.016. Is that minus 1.6? Oh, sorry, I'm not multiplying by 100. Minus 0.0016 newtons. Now, is that the answer? No, because that's not the drag force. What is that answer I just have? And it's not the weight either.
That's the force.
Yeah, what would you call this? Like, it's not the drag, it's not the weight. Yes?
The thrust? It's the opposite of the drag.
Oh, the thrust. It is not this either. No.
Maximum drag.
It's not this.
Average.
It's not quite this. In Newton's second law, the F represents the total force. The total force. So what you're saying here is that in total, the force downwards will be 0.0016 Newton. That's the total. Why am I saying total? Because it's made of two forces, the weight and the drag. In other words, you can say that mg minus d should equal 0.0016. That this is 0.0016 newtons bigger than this because it's heading down with that much force. So this is a little bit bigger than this. This means we can get d equal to mg plus 0.0016. That is 0.1, 9.81 plus 0.0016. So what's that now? That's 0.981 plus 0.0016. 0.9816 newtons is the drag, or rather, to be more precise, the average drag force. Now, students usually find this question a little bit confusing because it uses this formula in a way that makes you think very carefully about what the F is. The F here is made of two forces. The key lesson here is that in F equals ma, this is always a total force. It's never really the force for one of the things. It's always all the forces put together as a total single force. So because I got this answer, it means I know that this is a little bit bigger than this. A little bit bigger. And so I can work it out. Yeah? Write this down carefully.
But you said that we can't use 9.81.
Yeah, for the acceleration. But what I'm actually using here is the formula for weight. And that's always true. The formula for weight is always equal to mg if you're on the earth. But what's not always true is it's not always true to say A equals G, because it might depend on if there's other things slowing it down, or stuff like this. Okay, did you write this down?
Why is it positive 0.0016 and mg minus d?
Yeah, and the only purpose of the minus here is to tell me it's pointing down.
Oh.
So I simply know that this should be a small bit bigger than this, meaning that this minus this should give me the 0.0016. This minus's job is to tell me the direction. I know that it's going down, so I know that this must be a bigger number than this. How much bigger? That much bigger. I see lots of thinking. It's good.
But when you switch side, it's still positive.
My drag answer at the end, is it positive or negative? Positive. Should it be positive or negative? Yeah, why? Because it's pointing upwards.
Okay.
Seems legit.
If you do it the other way around, it's the same, right?
Yes.
What do you mean by the other way around? What?
Up is positive.
If you do it the other way,
Up is negative.
down is positive, you'll get all the same numbers, except in your system, you should be expecting a minus answer at the end. Because in your picture, you've called that direction minus and this direction plus. Yeah. Yeah. You're writing that down?
So is...
See, there's always one student unhappy with this plus and minus.
No.
Yeah?
I was thinking about the weight. What
Yeah.
happens after you minus the weight minus the drag? So the remaining force is...
Yeah. The remaining force is how much force is actually pulling the object down.
Oh,
It is possible it is possible for the drag force to be bigger than the weight. When a person opens a parachute, you know, the parachute when you jump out of the plane, when the person opens the parachute, at the beginning the drag force is greater than the weight. So there's actually a force acting upwards. Now you might think, oh, this force acting upwards, that means the person then will move upwards. No, what happens is as the person's falling and they open the parachute, the force up will be bigger than the force down for a short time. This will actually slow the person down because he's decelerating in this direction. But then what will happen is the forces will balance and then he'll fall at a constant speed. So, you know, you might think, oh, the weight is always bigger than the drag, but no, the drag could have been bigger than the weight. In this question, the weight was bigger than the drag. And I can see that because I got the minus here. It's acting downwards. It's hard to imagine for this that the drag could be bigger because then it would, you know, come out of the tube, which you wouldn't expect to see. Yeah. Did you all write this down? You have all of this written down? Yeah. So if you have, I think that was the last example, so I just want you to try for a couple of minutes, have a look at the questions that I gave you there. Got it? Yeah.